Hello, I'm Ling Luo from the SketchX Lab CVSSP at the University of Surrey. I'm going to present our work, 3D VR Sketch Guided 3D Shape Prototyping and Exploration. 3D shape modeling is labor-intensive, time-consuming, and requires years of expertise. To facilitate 3D shape modeling, we propose a 3D shape generation network which takes a 3D VR sketch as a condition. This network can generate a variety of shapes that align with the input sketches, while exploring different design choices. Specifically, the network is conditioned on a sketch and a noise vector sampled from unit Gaussian distribution. This setup enables us to sample shapes continuously and interpolate between them. We are aware of only one fine-grained dataset of freehand VR sketches, which we use in this work. Working with this dataset presents several challenges. The first one is the sparsity inherent to human sketches. Due to the sparsity and abstract nature of sketches, strokes can be interpreted differently. The second challenge is the issue of misalignment between the sketches and the corresponding reference 3D shapes. Lastly, the dataset's limited size is a constraint, as it contains only 1005 sketch shape pairs. This lack of data is particularly notable when compared to the size of typical shape datasets. Our first goal is the fidelity to the input sketch, which means the generated shapes should follow the overall structure of a quick VR sketch. Considering the sparsity of VR sketches, a single 3D shape may not match the user's intention. Therefore, we advocate for generating multiple shape variations that closely resemble the input sketch. Finally, the results should be geometrically valid. Even when presented with a desktop sketch as input, our method is capable of generating valid chair shapes. To achieve these goals, we train a conditional normalizing flow, referred to as CNF, in the latent space. During the inference phase, the encoder maps the input sketch to an embedding denoted as E. Then, we sample a random noise from unit Gaussian distribution and feed it into the CNF, conditioned on embedding E, which yields a shape embedding Z. The decoder then decodes the embedding Z to the ultimate shapes. The decoded 3D shapes are represented with signed distance functions, referred to as SDF. The signed value SPI of point PI indicates that the point is inside or outside the surface. In general setup of training SDF decoder, the network is driven by a SDF loss to closely resemble the ground truth shape. The SDF loss regresses the predicted SDF value to the ground truth value SPI, where NS is the number of sampled points. Since our objective is to ensure the reconstruction closely resembles the input sketch instead of the ground truth shape, we design a sketch loss on top of the SDF loss. Given that a sketch is a sparse representation of a 3D shape, the intended 3D shape surface is expected to lie in the vicinity of sketch stroke points. Therefore, the predicted SDF value of those points on sketch strokes should be close to 0. Minimizing the sketch loss motivates the network to generate results that are closer to the provided sketch. Here we show more generation results. For more details, please refer to our paper and project page. Thank you.